Hello everyone, my name is Logan. Welcome back to the lecture hall. Today we're covering section 4.7, Optimization for our UCI Math 2A Single Variable Calculus course. First off, what is optimization? Well, optimization is maximizing or minimizing quantities to have the optimal outcome. Some of the problems we will run into are problems such as maximizing our area with a certain amount of materials, or maybe minimizing cost problems, and these are all optimization problems. How do we do this? Well, just like most of the sections at the end of this course, because we only have one more video after this for the UCI Math 2A course, is there's a list of stuff we have to do, and once we do it, we solve the problem. So, let's see, what do we got? Understand the problem. What does this mean? Well, read it fully, read it out loud, preferably. I've already explained why reading out loud is better in 3.9 related rates. But understand what the problem is asking for. Are we trying to maximize area? Are we trying to minimize the area? Whatever it may be. Second, draw a diagram. Pictures make everything better, or at least in math. And so draw a diagram and it will help clear up what you're looking for. Third, introduce notation. So what do I mean by this? You need to give variables to certain quantities you're looking for. You can't just do like question mark equals question mark times question mark. No, you need to find the quantity you're looking for, whatever that may be. I'm going back to area again because those are our most common problems. But if you're looking for a max area, you maybe make your area equal to A. And then second, you express your quantity you're looking for in terms of symbols. So I put this Q, but it's quantity. It's whatever you're looking for. So you have, as I said in the previous step, oh, we're dealing with area, so that's big A. Well, area is equal to base times height, if we're just talking a cube, or not a cube, a square, a rectangle, whatever that may be. But area could be 1/2 base times height for a triangle, and that sort of thing. So, we need to express our quantity in terms of more variables, more symbols, to make it easier. Fifth, express Q in terms of one variable. So once you get it down to one variable, or once you have your A equals B times H, you then need to find what that is equal to in one variable, in terms of one variable. So what do I mean by this? Well, if you have your area is equal to base times height, and then your base is 2 times greater than your height, maybe area equals base times height, that's the same thing as saying is area is equal to 3 times height, 3h. And why is that? Well, because if base equals 2h, and then area equals base times height, then area is equal to 2h times h, which is equal to 2h squared. So, I was completely wrong. It is not 3h. It's 2h squared. But you can see, it's hard to just do it in your head. I tried to just do it really fast in my head, and I messed it up. So that's why you want to write stuff down, draw a diagram, whatever it may be. And after you get your quantity in terms of one variable, you find the absolute maxes and mins of your problem. You need this because that will be the optimal points where something works. That's where you can find, oh, at h equals 10, our area will be maximized with the amount of supplies that we have, whatever it may be. So that is the general strategy for these problems. So we're going to go over one last topic, and then we're going to do one of them so you can see. So I mentioned we have to get our absolute maxes and mins to solve our problems. But how do we do that? How do we know if something's an absolute min or an absolute max? Well, we have the first derivative test for absolute extreme values. Suppose C is a critical value of a continuous function defined on the interval I. If f prime of x is greater than 0 for all x less than c, and f prime of x is less than 0 for all x greater than c, then f of c is the absolute max value of f. So what is that saying? That's saying if we take our x, y coordinate, it's saying f prime of x is greater than 0. So that means the function is increasing until f of c, which will be somewhere around there. And it's increasing for all x less than c, because f prime of x being greater than 0 means the function is increasing. And then it's saying, and then when x is greater than c, f prime of 0, f prime of x is less than 0, which means it's decreasing. And this will be the absolute maximum for our function. So then, if f prime of x is less than 0 for all x less than c, and f prime of x is greater than 0 for all x greater than c, then f of c is the absolute min, and it's the same sort of deal, except here it's a decreasing function until it hits c, and then it's an increasing function. So it makes an absolute min. And so this is all well and good, but I haven't really talked about optimization, nor have I actually done a problem. So optimization is an incredibly important part of the field of math, but also a bunch of other fields. You use optimization for, I don't know, cost analysis, whatever it may be. So this is a very important section, and now let's transition to the practice problems so you guys can actually learn how to do basic optimization. Now to the practice problem. We're doing number 15. If 1,200 centimeters of material is available to make a box with a square base and an open top, find the max possible volume. Okay, so now we go through our checklist. What are we trying to find? We are trying to find the max possible volume with 1,200 centimeters squared of material. Okay, what's next? Draw a picture. So we have our box. I'm a math student, not a... That's a horrible box. But we draw our box, and then we find, okay, length, we have our width, our length, and our height. And then we know volume is equal to, well, first, hold up. Next step. What are we trying to find? We're trying to find the volume. So we're going to express everything V. That's what our number of interest is. So volume is equal to length times width times height, because it's just a rectangular prism. And it says a square base. So this length is equal to the width. So this is equal to W squared times H. Okay, so all we need now is to find W squared and H. The other thing is it says our perimeter is equal to 1,200 centimeters of material. And where do I get that? It's because this is 1,200 centimeters squared, and that gives us an area of useful material. So then that means our surface area for the cube without the top is equal to 1,200. And this is going to be equal to, well, the one base, which is W squared, plus 1, 2, 3, 4 walls for HW. Okay, and is that it for our area? Yes, because this top of the box is open, so we need 0 material to do it. And then next, what was the next step? Well, we wanted to solve it all as one variable. So we want to just figure out, we want to get rid of our H and just solve for W, because that's easy. So we get 1,200 minus W squared is equal to 4HW, and then we divide by 4W, and we get H is equal to 1,200 minus W squared, all divided by 4W. Okay, that's not too bad. And now now we have to plug in our H into our volume equation, this W squared H, and we have to do the derivative. We have to find the derivative of it because we need our local maxes and mins. Okay, so we have volume is equal to W squared times 1,200 minus W squared, all over 4w. And it's like, oh, that's going to be a gross derivative. Well, distribute this stuff out first. We get w squared times 1200, and we get rid of 1w, so we get rid of 1w there, and then we send this w to each of them, and then we get this is equal to 1200w minus w cubed, all divided by 4. Okay, we take the derivative, so v prime is going to be equal to, well, 1200 w divided by 4 is just 300. So we get 300, right? Because power rule, w goes away, minus power rule 3/4 w squared. Okay. Now we need to find our local maxes and mins. How do we do that? Well, we set this equal to 0. So we're going to set this equal to 0. To make it easier, we're going to multiply by 4/3. Why do I say multiply by 4/3? Because it will isolate this w squared, so it's by itself. So we can just get rid of that, and then we do 4/3 times what 300 is just 400 minus w squared is equal to 0. Then we get w minus 20, w plus 20, and we find that our local maxes and mins are 20 and negative 20. So then, normally, we'd have to just check, oh, which one works? Well, here it's pretty obvious. Our normal just 20 works, because we can't have a negative distance, a negative width. What is a negative width? It doesn't really have a definition. I mean, maybe in physics, I don't know. But for our purposes, it doesn't have a it's not defined, so we're just going to take our width to be 20. Okay, well, where do we go next? We plug it in to our perimeter function, because we know 1200 is now equal to 20 squared plus 4h times 20, which is equal to 400 plus 80h is 1200, and then this goes to subtract 400, we get 800 is equal to 80h, divide by 80, divide by 80, we get h is equal to 10. Okay, we're almost done. We found our width and our height. Now we just plug it into our volume. Well, what is it? Volume is equal to length times width times height, or width squared h, which is equal to 20 squared times 10. Which is equal to 4,000. And then we're almost forgetting something. It's not equal to 4,000. It's equal to 4,000 centimeters cubed. This is just like related rates in the fact that you have to put units. Your professor will mark off points if there are no units, because they're asking about quantities with units attached. So whenever you see units, make sure you add them. And this is the general strategy for optimization problems. You take it and you follow the 6-step checklist, and then you end up with an answer that's correct. So that's all I wanted to cover for the video today. Have a great day. Thanks for watching.